All right. So project one, what was the problem? We had to land aircraft on an aircraft carrier, given a runway of 2,500 meters. Obviously, don't want the aircraft to fall off. That'd be a fail. Also, don't want too many forces on that aircraft that cause any internal damages. And also reducing the acceleration so pilots don't feel a significant amount of G's. That'd be too much. Might cause them knockout, might cause them harm, even death, which would be a tragic event. Moving forward, given a model of the system, I transferred that into a free body diagram, spreading it out to look at the internal forces so I could develop governing equations from given characteristic equations that have been known. Also, lots of givens here so I can apply it out through mathematical methods. I developed the following governing equations, as you can see in the middle. From here, there's two options. You can either go with transfer functions, or you can look at state space. There's positives and negatives to each. I originally tried a transfer function. One of the issues with this is to get it into Simulink, you have to have the right form. And while I was able to develop a transfer function for mass 1 and mass 3, mass 2 being connected to x1 and x3, the math that I had to do to rearrange it into a transfer function, I wasn't able to get it into the exact format that I wanted to. So that was difficult, but a better approach is actually to go about doing it with a state space model, going ahead and declaring the state variables. We know that, x1 dot or v of 0 is either 64, 35, depending if it's on the F-18 to the UAV. And with that, we can build out a matrix once we declare the state variables and rearrange it. And with the input of, as I mentioned, x1 dot, that can be inserted as an input instead of using a step function, as you would probably likely have to do with a transfer function. And with that also, y, we can have y equal to x1, which is the output, which is the displacement of the aircraft carrier, which is what we're ideally looking at. Moving forward, this is how I did my Simulink setup. I have from the free body diagrams I made and from the government equations I got from that, I have two systems because there's two pairs of them that act with the ropes. I got the position at a time out of this because y equals x1. And from there, I could take the derivatives of that to get velocity and acceleration. I also had a filter because as I found in the acceleration, there was very high frequencies that was disrupting it, making it very hard to see the G's experienced by the pilot, which is a very important graph to look at. For part A, with the F-18, I found a KD value of 1,000. I was able to slow this aircraft down before it reached the 2,500 meter mark. The velocity profile looks reasonable as well, as you can see here, as I mentioned, with acceleration. Higher frequencies are disrupting it, so I can't truly get a good look at what it feels like. Of course, in the future, given more time and more expertise and more help, I would definitely look way more into the accelerations felt by the pilots because it's very important. Very expensive investment, and of course, for the sake of the human being, we don't want anyone getting hurt. Likewise, with the UAV, we have similar graphs. The only difference really being, of course, we have a different damping coefficient. It's less. That'd be expected considering the mass is less. And with that, with the mass being less, it reaches a steady state at a sooner distance. Part C, I did some mathematical calculations to figure out the max distance that's L could be for the max force, the max damping force, because that's what we're replacing here with the more newer technology. You can see F equals KDX, or velocity is replaced with F equals mu A V over L. What I did is in the state space in row 6, column 6, I simply replaced mu A over L to where KD previously was. And with the mathematics, that works out pretty well. Here's some of the responses I've seen for part C for the F-18. It actually reaches a state response much sooner than the older system, which is good. You can also see more of a sinusoidal pattern from it, which is not necessarily a bad thing. Showing more energy kind of more sparingly used. So there's not as much impact on these aircraft. A similar story with velocity and acceleration as with the past examples. Likewise with the UAV, this also reached steady state at a sooner point. And with that, the velocity versus time graph looked good. And the acceleration versus time graph, same story as other graphs. And you can see here, here's my appendix for the MATLAB code that I used to insert into the Simulink with all the mathematics, and all the state space matrices are listed here. Thank you very much.